So we are very proud to host two great researchers from Cineca. We have Domitilla, that is tech leader and researcher with Cineca, and she holds a PhD in mathematics. And we have Michele as well, also tech leader at Cineca and a PhD in material chemistry. So the stage is yours, and thank you very much for being here.
Thank you, all of you, for joining this session. And as you may see from the title, we're going to tell you how to harness an HPC infrastructure for your Gen AI workload going from training to inference. So before starting, I just want to tell you a few words about the infrastructure behind our tests, which is Leonardo, and in particular Leonardo Booster Partition, which has more than 3,000 nodes. Each node has 4 NVIDIA A100 GPUs with 64 gigabytes each, and is the 10th most powerful supercomputer in the top 500. And it has more than 300 teraflops operations when computing in BF16. So all the tests that we will show you are done on this HPC system. So first of all, we start with the training part. So how can you scale your AI workload on more than 1K GPUs when you have an HPC system? So first of all, the first non-trivial question that you're may asking is, why should I care about that? Why should I care if I have a perfect PyTorch code to optimize that for more than 1K GPUs? Well, let's say that is really non-trivial, because you may have a perfect PyTorch code that converges perfectly, that has a perfect loss, and that it behaves really well on a bunch of GPU, let's say 2 GPUs for 8. But when you scale to 1K GPUs, then you may have totally different numbers. You may lose throughput, you may lose token per second, you may lose the number of floating point operations that each GPU is able to do because of communications, because of wrong hyperparameters you're using, and because maybe you are not harnessing in a correct way the network topology of the HPC infrastructure. So I will show you some tests to make you aware of the differences that you may have between a perfect optimized PyTorch code or a Gen AI workload and one that is not fully optimized for an HPC system. So first of all, maybe several people are already aware of how to go from a single GPU to a multi-GPU setting, but just give me 2 slides so that we're all on the same page. So when you have a small model and you want to train that on, let's say, more than 1 GPU, the easiest way to do so is through data parallelism. So basically, you're copying your model on all the GPUs are available, and you're just splitting the data. What does it mean? It means that you have, during the training, just a bunch of collective communications. So all the GPUs involved in the training need to communicate with all the other GPUs involved in the training, but just a few times. So this is something that cannot be used anymore when you want to train a large language model. The answer is quite trivial, and it's because of memory problems. So if you want to train a 7 billion model on the GPUs I was showing you before, you cannot do that without you splitting the model on multiple GPUs. And this is why we go from data parallelism to different types of parallelism. So fully sharded data parallelism and model parallelism. I don't want to give you a lot of details of these types of parallelism and how do they work. But what I would like to stress is that with FSDP, You split the model, you split the optimizer, you split the gradients on multiple GPUs, and you have several collectives communication. This means that in this case, as in the data parallelism case, all the GPUs involved in the training are communicating with all the other GPUs involved in the training. But this now happens more frequently than in data parallelism. And then, if you want to go to model parallelism, what happens is that you're splitting the model, but in this case, instead of making all the GPUs communicating with all the other GPUs, what you're doing is that make some GPUs communicating with some other GPUs. So not all of them are involved in the communications. And you are right now guessing why I'm stressing this point, but we will see it in a while. So let's start with this first example. So here you can see an LLM training. It's an 8-bit dense model. And here we are showing the weak scaling. What does it mean? When we double the number of GPUs, we are doubling the global batch size. So the number of compute that is done by each GPU is almost constant when you go with a higher number of GPUs. So if you look at the blue plot, you see that the blue plot is almost constant. And there we are using model parallelism. What does it mean that when you go from, let's say, 16 GPUs to 1K GPUs, that plot is constant? It means that the network of the HPC system you're using is stable, so that the communication there is not a bottleneck. If you look, for example, at the red plot, what happens is that, first of all, the performances are lower than the blue one. Second one is not constant. There, you may encountering several issues in the communications, and there you have a lot of collectives communications instead of P2P communications. So remember, the blue one GPU is communicating with another GPU, the red one, all the GPUs are communicating with all the other. So this is something that you need to take into account when you go to 1K GPUs or when you're using really a high number of GPUs. The second thing that I want to show you is strong scaling versus weak scaling. So we were saying before that weak scaling is basically, okay, I'll double the number of GPUs and I double the global batch size. While in the strong scaling, basically, you're just doubling the number of GPUs without doing nothing else. Okay. So if you look at the first part of the plot, you can see that up to, let's say, 128 GPUs, both of the plots behave in a quite similar way. But then let's zoom in the last part of the plot. So when you go beyond 200 GPUs, the strong scaling start to behave in a worse way than the weak one. And this is perfectly in line with what we expect. And this is because their communication becomes to be a bottleneck. So you are communicating more than the computing part. So for example, this is extremely useful because the global batch size is an hyperparameters that you don't want to adjust based on the number of GPUs. So you would like to use a fixed GBS because you have done scaling laws with that GBS. You know how the model behaves with that GBS, and you don't want to increase that. So it's important to do strong scaling to understand the maximum number of GPUs that you can use without wasting too much time in communicating instead of computing. But if, for example, you can increase the GBS you're using, then what you can see is that you can gain a 7% of efficiency. So GBS here is the bottleneck, and it confirms what I was saying you before, so that here you are communicating more than what you're computing. So another hyperparameter that is extremely important for the throughput is the sequence length. So as you can see, the blue experiment is with a sequence length of 8K and the other one with a sequence length of 4K. The one with 8K has a higher efficiency because there we are activating another type of parallelism that helps in preserving the throughput. So a higher sequence length enables us to have a higher efficiency, so wasting less time in communication and using more the GPUs for the compute part. Okay, last thing I want to show you is the throughput stability. So when you're training an LLM, you need to do a really long run. And this is why you need to understand whether the behavior of the token per second generated of the teraflops operations that you have is stable through the run, or if at a certain point it starts to oscillate a lot. And this is why something that you need to look at before going for a long run is the throughput stability of your run.
Thank you. And now let's go to the other end of LLM spectrum, let's say. So it's inference. And we have an HPC center, so we have plenty of GPUs. And a lot of stakeholders asked us, let's build an inference endpoint, so something that can host a large model, and we can use them 24/7, etc. It is, for us, it's kind of a new endeavor, and we tried to tackle this problem, starting to think of what makes a good inference point, at least in our knowledge. So first of all, there's, of course, a simple API exposed to the outside world. It needs to be up, ideally 24/7, in a sense that I could, send requests to my model whenever I want, in theory. So in order to do this, I need to have like automatic restart on failure, fallback models, etc. Everything that would enable this 24/7 uptime. I need, of course, fast generation. I want an efficient inference endpoint, so with good metrics, let's say, low latency, high throughput, etc. I kind of need to manage also the load that this inference endpoint is, faced. So I probably need some form of auto-scaling in terms of, resources management, some kind of load balancing. I need also, of course, observability. So all the stack that's need to monitor the health of the endpoint, the nodes, the models, how many tokens are generated, by who, etc. And I also kind of need some type of model lifecycle management. So we basically live in a world that every 2 weeks there's a new large model that is the new hotness or whatever, and we kind of want to have it, or at least be able to have it. Well, we live in HPC, in a classical HPC, which means that we have, we use Slurm, which is, let's say, a framework to submit jobs in a queue that last for a fixed amount of time in nodes that are air-gapped, so we don't have any connection to the outside world. So, for example, a simple API exposed to the outside world, well, no luck, air-gapped nodes, so no way, it stays there. 24/7 uptimes, well, no luck also there, because we have Slurm, which means that the maximum amount of a job that can run is 24 hours, then it needs to stop. And also, you submit the job, then you wait for the job to start. And if it's like, high traffic in the HPC system that we have in Leonardo, well, tough luck, it stays there for a while. Fast generation, well, luckily Leonardo has around 3.5K GPUs, so we can define a topology to make this thing go fast, so this is not an issue. Load management, again, Slurm, because when you submit a Slurm job, you define exactly the number of resources that you want. So if you saturate your model, well, the job breaks, and that's it. The job breaks. You don't have an inference endpoint anymore. And then model lifecycle, again, Slurm, in a sense that I submit a job, the endpoint stays up, I cannot do anything on it. It just stays there. If I want to change a model, I have to, break everything and restart the job again. So this is our situation, unfortunately. And if you remember Apollo 13, it's like putting a square peg in a round hole in a certain sense. So we have to make this inference endpoint using, HPC system and only Slurm, Singularity, not even Docker, Singularity, air gap nodes, queue system, etc. So let's start thinking step by step, like LLMs do. So what do we need? First of all, we need to create a cluster. So a pool of resources, of GPUs or nodes or whatever, from which to start the models. And we kind of need something to monitor the state of the cluster and something to actually start the model servers inside the cluster, given a config file. We also need something that routes the communication from the outside world to the internal Leonardo nodes, and also the opposite. Well, the first two things is decide the technology. Ray, it's the most obvious choice for a cluster in the sense that I can say, okay, I want 10 nodes, I set up a Ray cluster, and I can do whatever I want inside there. And in terms of monitoring and starting the cluster and health checks, etc., we use Airflow. I build a DAG that checks every, 2 minutes, 3 minutes, the health of the cluster. It starts the LLM there with serve run, and so on and so forth. And also, we need to decide where to put this thing, because we have Leonardo, which is air gap node, etc., which is the correct place to put the Ray cluster, because it has GPUs. But we also have a cloud system without GPUs, which is kind of open to the outside world. You can connect to it. Now we just need something that connects the two. And our system administrator found us a tool, it's called Chisel, that lets you do some type of reverse HTTP proxy between Leonardo and other cloud. So you need a client on Leonardo and a server on the cloud. Let's go a little bit in detail. This is the very high-level way that we built our inference endpoint. So you have a controller on the virtual machine, which is basically made of Airflow, so a certain number of DAGs, and the Chisel server. So the Airflow checks the cluster state, submits Slurm jobs, starts the actual serving of the model through SSH, SBatch, the usual also Slurm commands, and so on and so forth. We also have the model configs, so the YAML files for a serve and the VLLM parameters to actually start the models. We expose the 8000 port through this Chisel server. We also handle some type of authentication. And then we have an executor part, which is on HPC, which is basically a gigantic SBatch script, which starts the Ray cluster through Singularity, everything with containers. They need to run on a head node and worker nodes. And then inside that, the Airflow actually starts several instances of serve run, so basically VLLM servers that expose a port with the reverse tunnel. It's actually open to the virtual machine and then to the outside world. So we have the usual API clients with B1, chat completion, metrics, and so on and so forth. There's all of this thing. There's plenty of pain points that we're going to actually dissect a little bit, because I'm actually going a little bit into details of all of this. So let's start with the part that I know the least, because I'm not a system administrator, but it is the communication part with this Chisel reverse proxy. So you need to do two things. Install it on your cloud virtual machine, which has the server, and then have a client, which is basically a bunch of code lines that are inside the SBatch script that start the client. What the system administrators actually have done on Leonardo is open for us one port, 443, which we funnel every communication from the inside world to the outside world and vice versa. So basically this HPC proxy controlled ingress and egress, all this communication between this single port. Then what happens is that the actual Ray serve only exposes localhost port 8000, because we chose so, inside the private compute node. It goes inside this HPC proxy. It goes out. It goes in our virtual machine, which we have the server, which opens the virtual machine IP and the same ports, plus the array dashboard, and the client, right, can simply connect to the virtual machine. So, first exception or regular HPC use case. Then we have the second part, which is the Airflow DAG. This is just the schema of the DAG, more or less. Every 2 minutes, just one DAG. We check the cluster. If it's not even up, it starts one, and then it waits. If it's up, it checks if the LLMs there that we want are up, and if not, it copies the config files, so the single VLLM-like config file plus the reserve config file inside Leonardo, and starts the LLMs. Here, hidden here, there's also one technicalities. In order to access Leonardo, you need an SSH key, right? And by design, they last 12 hours, full stop. You realize that this is basically impossible to have something that needs to stay up for months, every 2 minutes checks, so we need to ask the system administrators to make us a long-lived, basically SSH key. So it's non-expiring, dedicated to a specific user for which we can access the machine with, but it's just for this project. So it only has permissions to do these things. With this, then you can do SSH, start jobs, and so on and so forth. Then let's go to the array part, so the script, which is basically a little bit, I think of it like nesting dolls, because you have one script that sets up the number of nodes and GPUs that we want to use. This is still kind of a prototype. It works, but it's still a prototype, so it's 10 nodes, 40 GPUs. Then you have the node discovery. So you identify one head node and a series of workers. In our case, one head node and 9 workers. You have to log the IPs of all the nodes because you decide one is the head node, and inside the and with this you will start restart, and the other will be just the workers. The nodes don't start array straight away. They just set up a container. So we replicate the container in all the nodes using Singularity. Then we go inside all of them with Singularity instance. We go in. On the head node, we start restart. We log the IP, so the worker nodes, we do the same command, but inputting also the IP of the head worker node. When everything is done, we register that everything is ready for server run, and we log, this will be important later, all the environmental variables that we have ever set in this job, both the publicly available general ones plus the one that we used for the specific job, like the IPs of all nodes, the number of GPUs, Hugging Face cache, hub, air gap node, we cannot connect to the hub, so we had to previously download every model and so on and so forth. Then, of course, there's another exception here. We have jobs that last only 24 hours. This is not acceptable. The jobs go inside the queue system with priorities. And the priority is defined by how much you have asked previously, your quotas in the project, and so on and so forth. This is not acceptable. So we asked for a custom queue for 10 days, that lasts 10 days, with the highest priority possible. There was the option to actually have a reservation, so a certain number of nodes that are just for this. But this is a problem, which is maybe not obvious. If you have 10 nodes and one of them breaks, I cannot do anything because I just have 9 nodes, and I cannot just substitute another one. Instead, if you have a custom priority queue, you can always ask for 10 free nodes throughout the cluster. Of course, they can be located everywhere inside the machine, so the communication will be slightly more problematic, but at least we have something that actually starts immediately and almost all the time. We also needed a custom project with dedicated node hours because we have to account every type of usage and so on and so forth. So this is another exception on top of the others that I already told you. And then how to actually start the models. we have Airflow, we have a array server, array cluster that is working. Array cluster, what it lets us to do, it lets us to simulate some environment that has some sort of auto-scaling or replica management or something like this, because at least we have this pool of 10 nodes in which we can do kind of whatever we want. So the part of the Airflow pipeline that I showed you previously also starts the actual VLLM models, let's say. So we have the model ID, all the arguments, also the replicas that we want to set, the minimum and maximum replicas that we want to set for every models that we want in case of overloading the models. So we created these YAML files, the configuration files, that need to be fed to this larger config.yaml file, which is the actual array-serve configuration file. We copy these to the HPC machine, to Leonardo, using our custom key, etc., that can do SSH, etc., the reverse tunnel, blah, blah, blah. And then we go inside the head node container and we start a server run. The head node container knows all the other workers IP. It's basically a cluster. So we start it on the head node and then Ray figures out whatever to do. Using VLLM with Ray backend. Funny story, we actually found that VLLM doesn't come with Ray native anymore, so we kind of have to rebuild the VLLM image on the container from start. And you also find a small bug in multi-node VLLM with Ray. So we tried to patch that. So we also built like a very complex script to build a container. In the end, all of this exposes, the usual API, VLLM API. There's V1 models, chat, whatever. And with the reverse tunnel in the virtual machine, you actually can connect to the IP of the virtual machine, port 8000. The same port can serve multiple models, as VLLM does. So you just need to change the model ID, the name of the model that you want to use. At the time we are serving, we are testing it, and we are serving like 3 models, for example, 3 small models, 3 Quen family models, around 30, 40 billion parameters. But we also tested the Quen 3.5 with 400 billion parameters, and it's kind of working. There's still some problem, but it's working. So what is still missing? This is just part of the story, because this is just setting up the scaffolding, which is pretty much complex still. We don't have any form of access governance at this stage. The entire virtual machine is behind a company VPN, but we need to find some API gateway in order to, give authorization, token rate limits, quotas, and so on and so forth. And we honestly don't know. Accounting and capacity. We need to also build the tokens, so to let them pay the users what they're going to use. We're not asking directly for money, but node hours. So we need to figure out how does a single token cost in terms of node hours, so a really small fraction, and actually check which user is using which models and what they are generating. Observabilities, usual stack, Prometheus, Grafana, MLflow, Langfuse for the traces, etc., which kind of is the easier part in a certain sense, because it's just a bunch of containers that I start in the virtual machine and I forget about it, more or less. And then, of course, portability. This is true for Leonardo, which has a specific way of handling communication, etc. We want to do this also for Lisa, the new partition, which has 800 GPUs. It's geared towards AI, and for the future Italia machine for the AI factory. Hopefully, the constraint will be a little bit more relaxed, and this craziness will be a little bit more simple. But we'll see. We're also working a lot on choice of the model and to make them work as fast as we can, as more optimized as we can, because we have GPUs, luckily, so we can really do hyperparameter optimization, topology optimization, stress test, even check if we want to really use VLLM. We also work with the NVIDIA, with the Dynamo, with their inference stack, which is Dynamo, and we are testing also this. But yeah, as you can see, there's a lot of stuff to do. And then we have a couple of take-home messages, first for the trading part.
Yes, so thank you. Okay, so as you may have guess from my part of the talk and from Michele's talk, HPC was almost made for training, let's say. But there are a bunch of things that need to be taken into account before training a large language model or a Gen AI model on an HPC system. And the first one is scaling, both weak scaling and strong scaling. And this is because you need to test the network, so the topology of the HPC system you're using, and also the tool that you're using for parallelization. Because it doesn't mean that if, let's say, some tool is working very well on an HPC system, it may have some issues or problems when you change the HPC system that has, for example, a different topology. And then we strongly recommend also to do strong scaling experiments that I was showing you before to avoid wasting GPUs that are almost used for communications instead of computation. This is because an optimized code, let's say, saves GPUs and money if you pay for GPU hours. And apart from the weak scaling and the strong scaling, something that you need to take into account is that how you design the model has an impact, a strong impact on how the model uses the infrastructure that you're training that model on. I didn't add slides on MOE models, but as you may know, MOEs are less optimized, let's say, for GPUs because they're really sparse models that are using less, are generating less floating point operations per second. You still have a good token per second generation, but if you look at the compute part, the MOEs are less, let's say, optimized than the dense models. The other thing is that the parallelization flags matter. This is a really important part. I just do a very quick example. So if you have 4 GPUs per node, for example, as Leonardo has, certain flags need to be equal to that number of GPUs per node. Otherwise, you're insisting on the communication of the intranode communication, and it slows down your code in a really significant way. So it is true, on one hand, that HPC was made for training, but there is quite an important caveat in the sense that the HPC system that we have nowadays have not been extensively tested on AI, such AI workloads. What does it mean? It means that we do not have standard benchmarks, AI benchmarks for HPC system. We do have obviously large language model that we can train, Gen AI model that we can train, but there is no AI benchmark for HPC system recognized by the community. And this is something that I think can really help users and communities to choose the proper HPC system. So as HPC and AI community, we should really work on that.
Okay, and quoting Domitilla, HPC systems are not made for inference, unfortunately, but this is what we get, which is not nothing, which is plenty of GPUs, so we try to do this. Tools are not really the problem, it's industry standard. It's more communication, ownership, permission, billing, etc. The usual stuff. Everything theoretical is really good, then you put down to earth and you need to do all this piping. Also, to our knowledge, this is also a big problem for many HPC centers. And we are charting, unknown territory here. There's many different options. I heard about some HPC centers that decided to detach some nodes and open them to the public, whatever. Or, using cloud resources. Of course, we would love to have Kubernetes on super clouds with zillions of GPUs, but we don't have at the moment. And so we work with this, which is, again, nothing to scoff at, basically. And that's it. Thank you. Thank you very much.
Can I use? Yeah. Okay, thank you very much, Domitilla, Michele. Super interesting talk, and I'm sure there are plenty of questions, so we have time for 2 or 3 of them. Yeah.
Hey, thanks a lot for the presentation. Super interesting. Just one on the training side. You just mentioned about MOEs, so maybe I've lost a bit of touch on the training side. But usually, you want to have obviously lower flops when running the model, but you should be able to have just like bigger batch size. Or at least that's usually what we do inference side. So I was really interested, like training-wise, how would that be an issue if you just like increase the batch size so that basically you eat that sweet compute bound spot?
Okay, so let me make a comment on that. So you can look throughput obviously as TFLOPs or token per second. If you look at the token per second, you have really good scalability with MOEs. It means that even though you have a higher communication than on the dense model side, because you have expert parallelism, you have more, let's say, sparse models, this does not have an impact on the behavior. But you're not able to reach the same TFLOPs as you reach with the dense model if you use the same parameters. So for example, if you, the more sparse the sparser is the model, the lower throughput in terms of TFLOPs you reach if you compare with the same hyperparameters. But then if you look at the token per second, for example, the sparsity increased the number of token per second that you can generate, and so it's kind of a trade-off. But let's say GPUs somehow are made for, let's say, dense matrix multiplication, so handling sparsity is more complex if you compare at the same number of parameters.
Thanks.
All right, we still have time for a couple more.
Thank you. Quick one about training. You mean pre-train, post-training?
Yes, pre-training.
Okay, so literally from scratch. And what about like the data management aspect? Like, because also at that point, cleaning up the data, preparing the data, do you have already that part solved? Or essentially, you have a prepared data set that you want to use, or also you do that part?
So we were focusing mainly on optimizing the training part, so optimizing all the hyperparameters. So we didn't look at the previous part, since this is not for, let's say, a production run or training an LLM from scratch, but it's just to be sure that our users and in the project we are involved, we are using the, let's say, the most optimized configurations that we can on our system.
Okay, thank you. And on the inference side, I mean, for sure it's not designed to do inference, and you did a great job to make it work, at least. So you definitely need an LLM gateway or an AI gateway in front. Yeah. At the same time, it's outside HPC, so it should be reasonably trivial for you to configure that. Hopefully. Hopefully, but I mean, given, no, I mean, as soon as you're looking about the scalability now, even Dynamo and similar, I think that you're going to hit also other challenge about the point, the fact that you want to keep some sort of transparent allocation about every node, because at the point you might want to be more topology aware about how you place the replica, because you do disaggregation and stuff like that. Yes. So at that point, I don't expect that the challenges could be VLLM versus Dynamo or LLMD or similar. It's going to be from a point of view more like how you really orchestrate all of this.
That's absolutely true. I know I'm speaking like an LLM, but that's it. This is true. This is true because all of this is kind of a proof of concept, let's say. Then we will need to dig a little bit more into this. This will be definitely a challenge.
Okay, we have time for one more question. Luca, you had one?
Thanks to the talk, it was great, and I find it incredibly fascinating that like there is like a line where somebody says, okay, maybe we should make Leonardo like run on inference side, and even if that wasn't meant to be. I've worked a bit like mostly as a consultant in a small company, and then I moved on to an enterprise setting, and I did realize there are lots of challenges related to policy, access to certain nodes, etc. And I see that the same challenges popped up here because like the boring part is setting up the processes, right? But I wonder, and maybe this is a bit more of an open question, but why are they so hard? Like, isn't there like any open policy, open source, like permission or management system that you can set on top instead of writing glue scripts that like start race somewhere?
Well,
and also, why can't you use Kubernetes?
Because we can't. That's the.
But like by design, like hard requirement,
Yeah,
no
hard
K8s.
requirement.
Like, you don't like it.
Because it's.
Yeah.
Yeah, you
Okay.
basically have to stop the machine for weeks and then you restart it, which means other weeks to make
Okay.
it work, you know. Then we have like 2 months downtime and everybody will kill us, especially the JU. But I mean, you were. Yeah, then you were talking about, you know, why do we need all these quotas, billing, etc.
No, but I know you need them. The point
Yeah.
is how.
How?
I mean, do you think you need to build stuff from scratch, or can you start something?
This, honestly, I don't know, because it's a part that I haven't started to look into.
Okay.
If there's something or somebody that has figured this out already, fine.
Hit me up.
Yeah, exactly. Just please hit me out. But no, we don't need to write something from scratch. I mean, we have just used the technology that we can, open source, of course. We are, you know, public company, so this is what we want to use. And yeah, if somebody already figured out, we know some. I think at least other AI factories, other HPC centers, kind of worked on this. I think Lumi kind of figured out a way to convert. Lumi is the Finnish HPC center. Kind of figured out a way to at least convert, you know, in node hours what a single token is, some type of. But yeah, that's basically the thing.
Cool. Thank you very much, Michele, Domitilla.